forward and get rid of this. All right. Let's see. Part of this page is teaching, part of it has problems. So let's look at the problems. The first problem I see is number 1 under 3.2. Is that where you want to begin?
Yep.
Okay. Are they referring to a particular graph?
No.
Okay. Here, let me move up. So none of these first 4 questions are referring to any of the above graphs?
No, I don't think so.
Okay. I hadn't had time to really examine this that much, but okay. Explain how f prime of x could be positive or negative at a point of which f of x is greater than 0. Well, let's start with f of x and x. And let's draw a curve like that. Okay? Now, let's go down here, and we'll call this f prime of x. So I have 2 different charts, same x-axis, different vertical axis. One is the function, one is the slope of the function. What is the slope of that function throughout, from 0 to here? Is the slope positive or negative?
Positive.
Is there any place where it's not positive?
No.
Well, actually, I made a little bit of a mistake there. One could argue that that's negative, but you see why that might be negative?
Yeah, I do.
I didn't intend to draw it like that, okay? I did intend to draw it where it was all positive. Now, if I go back and draw this slope, well, f of x is still positive throughout, right? And yet it's got a negative slope from there to there. So whether or not the original function is in positive territory or not, the derivative can be positive or negative, depending on whether the slope of the tangent line is positive or negative.
What? Sorry, I just spaced out so hard there. I just had like 4 hours straight of sports, so.
That's all right. Here, hold on a minute. Let me see if I can make it a little clearer here. If I have a function that's like that, that function is positive everywhere, correct?
Yeah, correct.
What is its slope everywhere?
Positive.
Okay, so f prime of x is also positive everywhere. But if I have a function like this, what's f of x everywhere?
Negative.
No, f of x is in positive territory. It's above the x-axis. So when it says f of x is greater than 0, it merely means that notice the f of x axis is the vertical axis here. Okay, So with both my black line and my red line, f of x is positive. And yet one has negative slopes and the other has positive slopes. You see that?
Yeah, I see that. Okay.
Okay, so that answers that one. Now, if I want to answer question number 2, explain why f of x could be positive or negative at a point at which the derivative is less than 0. So I'm going to draw a line like that. What's the slope?
Positive.
And the derivative? Hold on. Let's start. Sorry, I didn't go in the order they were talking about. Let's start. In other words, this is the requirement. The derivative has to be less than 0. So there's a function whose derivative is negative everywhere, and f of x is negative everywhere.
Mm-hmm.
Well, if I go up here and I write in green, again, the derivative is negative everywhere. But f of x is positive everywhere because it's above the x-axis. That's what makes f of x positive.
Okay.
Okay. Differential calculus is a little bit like thinking in 2 dimensions. It's kind of like 2-dimensional chess. In other words, you always, and actually that becomes 3 dimensions because there's second derivatives also. So you're always being asked to compare first derivative graphs with the original function, and sometimes with second derivative graphs. And second derivative is really very easy. It's just the first derivative of the first derivative. Okay.
Mm-hmm.
Now, this stuff can be quite complicated, so I want you to stop me if at any point I lose you.
Okay.
Okay? Be sure to do that. You do not want to get lost here, because then everything that I say after that's just going to pass right over your head. It'll be all wasted time. So don't let me get to a point where you don't understand what I'm saying.
Okay.
Okay? I tell you what, one thing I want to do here that I do for everybody is to bring up this graph. Hold on a second. I gotta find it. Just a second. It's here. I want to go to calculus, and I want to bring up no, not that. Just a second. Bear with me here. This is the graph I want. I don't know why this graph is not shown to every single person that takes calculus. Let me minimize it just a little bit so you can see it for a moment, all 3 of them on here. Now, what you're looking at there is the original function, y, okay, versus x.
Okay.
Right below it, you've noticed that says y prime. That's the first derivative, and you'll notice that applying the power rule, that would be the first derivative, 3x squared plus 6x minus 9. And that's what that function looks like. and then go down and look at the bottom graph, which is the second derivative, which is merely the first derivative of the first derivative. In other words, if I took the first derivative of that, I would get 6x plus 6.
Okay.
Okay? And this is y double prime vertically. The x-axis is the same for all three. Now, one of the more important things you're going to learn, and I might as well start talking about it now because it applies to some of these problems you're doing, is that notice when the original function is increasing from there to there. Can you see my cursor?
Yeah.
Well, first derivative is in positive territory. First derivative is in positive territory from there to there. It's not increasing, but it's in positive territory, right?
Yeah.
Okay. So one of the rules for derivatives is that when your original function is increasing, the first derivative is positive, always. When your original function is decreasing, which it is from there to there, the first derivative is negative. It's in negative territory. See that?
Mm-hmm.
And when your first derivative starts increasing again, when your original function starts increasing again, first derivative moves back into positive territory. So this middle curve is the first derivative curve of the function. And if you look at the curve, it's a quadratic, so it should be a parabola, whereas the original curve is a cubic, which frequently look like this. They have a maximum and a minimum. In other words, they have a couple of extreme points.
Mm-hmm.
And there's a couple of other very, very interesting things about this. When the original function has a zero slope tangent line right there, in other words, if you were to draw the tangent line, it would be flat. First derivative is 0. Remember what the first derivative is. The first derivative is the slope. So anywhere on this original function, if I want to point at slope, I can go down to the first derivative and find a value. Well, the slope is clearly 0 there. It's also 0 right there.
Uh-huh.
So there's two places where I would say the first derivative is 0, at that point and that point. And that's certainly true. And now let's go down and look at the first derivative compared to the second derivative. Same rules apply. When this function, remember what derivatives are, is they're just a derivative of the previous function. It doesn't really matter that this is a first derivative and this is a second derivative. You can think of this as being the original function and this as being the first derivative. So again, the original function is decreasing from that point to that point. If I go down to its derivative, it's negative in that entire realm.
Mm-hmm.
When that function has a 0 slope tangent line, in other words, its first derivative is 0, well, my first derivative, or what's called the second derivative, is really the first derivative of what's above it. Well, it's 0. And then when this function starts increasing again, its derivative is positive. Okay?
Okay.
Now, as long as we're talking about this, you're going to learn this eventually. I don't know how soon, but let's finish our discussion. I don't want to leave this. This is too important. It's extremely important for understanding calculus from a graphical perspective. notice what happens right. Well, first of all, let's talk about concavity. Okay? That's concave down. You see why? That's what it's called, is concave down.
Mm-hmm.
This part, concave up.
Okay.
Where does it change? Right there. And that's called the inflection point. Now, what is true about inflection points? The second derivative is 0. If you go down from that inflection point to the second derivative, it's 0. So wherever concavity changes, your second derivative is 0. All of these rules you're going to have to memorize eventually. So all I'm doing is just introducing them to you.
Okay.
Now, notice the middle function only has one kind of concavity, and that's concave up everywhere. So there's no inflection point. So if I took the second or the third derivative, it would not have a 0 point. There's no concavity change there. All right, let's leave that and go back to our questions. If f is differentiable at a, must f be continuous at a? True or false?
F is yes, true.
Yeah, because of these three rules that they gave you. These three rules, these three rules at the top. In other words, a function is not differentiable if it's not continuous. So if it is not continuous, in other words, if I point to that point right there, can you see where I'm pointing?
Yeah.
It's not differentiable at -2. If I point to that point, it's not continuous there. It's not differentiable also. And if I point to that point right there, that is a corner or a cusp, as they call it. So it's not differentiable there either. So there's lots of functions where it's not differentiable at certain points. And that's a key consideration with calculus, is to figure out whether something is differentiable throughout its entire domain. Well, this function here, it's natural. It is definitely a strange looking function. And the only reason they put it there is to demonstrate to you that it's not differentiable there because it's not continuous. It's not differentiable there because it's a cusp or corner. And it's not differentiable there because it's not continuous either. All right, let's go down and look at number 4. If f is continuous at a, must f be differentiable at a?
No, because it could be a cusp or a corner.
Exactly. If I go back to this point right here, that's definitely continuous. In other words, the easy definition of continuous is, can you draw it without picking up your pencil?
Mm-hmm.
If you can draw it without picking up your pencil, it's continuous. There is a more mathematical definition, but we won't worry about that now. As long as you understand, that's the layman's definition of continuity, is if you can draw it without picking up your pencil. Well, I cannot draw that point without lifting my pencil, and I can't draw this point, but I can draw that cusp without picking up my pencil. So it's continuous, but it's not differentiable.
Okay.
You might wonder why, and that's where that second derivative function comes in. But if I tried to draw the tangent line, would I draw it like that? Or would I draw it like that? Or would I draw it like that? There is no proper slope at a corner or a cusp.
So would those technically all be true?
No, it's not differentiable. So if one were to ask, what is the slope of the tangent line at 0, at this point right here, it is not defined. There is no slope of the tangent line there.
Okay.
When you say something is not differentiable, that means there's no slope of the tangent line. Now, there's one other situation that let's talk about here, and that is where you have a vertical. Hold on a second if I can figure out how to do this. Wow, it's turning out to be harder than I thought. Okay. See this function here in the upper right?
Mm-hmm.
Well, if I were to trace the slopes, hold on, let me get so I can write on it. Well, I got a slope like that. That's a positive slope, positive, positive, positive. But when I get right here, what's that slope?
Nothing.
Does not exist.
Mm-hmm.
But it's really infinite. Okay? And notice what this says here, is that I approach 0 from the right, it's infinity, positive infinity. But if I approach 0 from the left, it's also positive infinity. Therefore, they really shouldn't say the slope doesn't exist. It does. It's positive infinity from the left and the right. Therefore, it does exist. It's positive infinity. The only reason they make this statement is because they're reluctant to say something is infinity. But that's really what it is. The problem is that you've learned all along that vertical lines have a slope that does not exist. Okay? It's kind of like saying, what's the limit of 1 over x as x approaches 0? Well, it depends. If x approaches 0 from the right, it's positive infinity. If x approaches 0 from the left, it's negative infinity. So it's correct to say that that limit does not exist because it's not the same from the left as it is the right. But this is different. This one, from the left, it's positive infinity, and from the right, it's positive infinity. So it definitely exists. What is it? Infinity, positive infinity. That's what the slope of a vertical line is positive infinity, regardless of what they say there. I don't like that at all. All right, hold on a second. Let me go down here. There's so much good stuff on this page to talk about that I don't really know where to. Now, we don't need to go through their example and solution. So we've done 1 through 4. Let's talk about 5.
Okay.
Hold on a minute. Use the graph of f to sketch a graph of f prime. Well, I'm going to do f prime above it rather than below it, merely because I don't have room below and I can't scroll down because I'm at the bottom of the page. So unlike the example where I gave you, where f prime was below f, this is going to be y prime, still x, and we're doing this one right here.
Okay.
So let's start from this point right there. Let's label the y-axis 2 and minus 2. What's the slope right there?
-1.
Okay, let's mark that point. It's -1 all the way to what?
-2.
On the x-axis.
Hmm.
So that's a solid line like that. And
Okay.
1. Okay. And then it's not differentiable at -2. So that's an open circle. It's not, the first derivative is not defined at -2. But from -2 to 0, in other words, from this area there, what's the slope?
Well, would it just be 1?
So that, whoops, got it in the wrong spot. Hold on a second. That's 2. Since we want to draw it at 1, we'll go from there to there. And notice that it is not defined at -2. It's also not defined at 0. So I've got open circles on all of this.
Yeah, because there's 3 possibilities, right?
Well, it's just not defined. In other words, this becomes a piecewise function that is not defined. F of -2 is not defined. F of 0 is not defined. And F of 2 is not going to be defined. So
Okay.
when we go from 0 to 2, we're again looking at a slope of -1. With me?
Mm-hmm.
And then when I go from 2 to 5, what's my slope?
0.5.
And we'll leave that open, or not an open dot, because it's actually defined there. In other words, that's not a cusp, it's an edge. And on an edge, the slope can be defined, and it is. So I'm not going to put a closed dot there, but I'm not going to do anything with it, okay? So that's the first derivative curve of this.
Okay.
Okay? Now, you tell me how to do the next one. In other words, again, let me draw the first derivative curve above. And let's see, that point looks like -1.5. And that point is at 1, a key point. And that point is 1, 2, 3, 4. So what's the slope from 1.5 to 1?
Hold on. It's
The easiest way to do this, Jake, is to find points that go through corners.
Yeah, no, I was just trying to do the math in my head.
What's
Is
the
it
slope of that right there? It's a straight line, so whatever the slope of that little portion is, it's the same slope as the whole line.
3/2?
Now, count rise over run for the point that I've circled.
So it's 3/2, right?
No, it's up 2 over 1. In other words, I'm going from this point here to that point there. They're both on corners of the grid, so I can measure them accurately.
Okay, that makes more sense.
I don't want to go from this point because that's in the middle of a grid point. I think that's -1.5, but I'm not positive. So look for points that are on the grid. There's another point on the grid. I could have used that one also. The key is just to make sure you can read it accurately. All right, so my slope from minus 1.5 to plus 1 is what? And how should I draw it on my y prime graph?
So it would start at 1.5, and it would be at 2, and it would go to 1.
What kind of line are we talking about?
Flat.
Horizontal?
Yeah.
Okay, that's what I was. This is the one part of tutoring math where it would actually be a little better if we were in person because I could see you draw the curve. And that's what this is all about, is drawing the curve. Now, that shouldn't be open, okay? Because it is defined at minus 1.5. It's a slope of 2. In other words, if I go down to that point right there, that's a slope of 2. So it starts out right at 2. In fact, maybe I should put a closed dot. I'm not sure whether I should put a closed dot there or just leave it ending. I think they both kind of mean the same thing. Okay. The only thing I know for sure is it's not defined at that corner. So it's definitely an open dot there. And between 1 and 4, what's the slope?
Between 1 and 4, it would be just 1.
Positive or negative?
Negative 1.
Okay, so if I go down to negative 1, then between 1 and 4, we know it's not defined at 1, but it is defined at 4. But again, the derivative curve looks nothing like the original curve, which they never do. They always look significantly different. Okay. One of the skills you're going to learn in calculus, and this is one of the more difficult ones, you won't get to it for a while, but if they give you the derivative curve to start with, figuring out what the original curve looks like. That's a bit of, I won't call it art, but it's certainly harder than going the other way. In other words, we went from the original function to the derivative function. It was pretty easy.
Yeah.
You had to read the slopes. Going from the derivative function back to the original, that's a lot trickier. All right, let's see. I guess that takes care of this page, doesn't it?
Mm-hmm.
All right, let's look at the next page here. Let me download it. I think it might work a little bit better. So how many kids are in your calculus class?
There's quite a few. We have 2. I think we have 2 or 3 periods of calculus.
Who's your teacher?
Mr. Moore.
Married to Miss Moore.
Yeah, we actually have 3 Moores in the building.
I know. I've met Miss Moore.
Mm-hmm.
At least I've met the wife of Mr. Moore. I don't think I've met the other one. Okay. Match A minus D with capital A minus C. When I looked at this originally, I couldn't figure out what the heck is that curve? What is this curve here on the left? What's that have to do with anything? Am I not understanding this? Here, let me zoom down a little bit because I need to bring in everything into the picture. All right. So my interpretation of this is these 4 black curves are the function and the 4 red curves are the derivative. And I'm to match up which one is which. Am I correct?
I think, yeah. That makes sense to me.
So what the heck is this thing on the left?
Yeah, I have no idea.
Oh, I get it. The thing on the left, below it, is y prime. Notice that below is all horizontal lines.
Oh, okay.
And
Jeez.
above it is all lines with slope, either positive or negative. But they're all straight lines. So when you take the derivative of a line with slope that's a straight line, you get a horizontal line, always. Okay? And I guess we could match that up also. And it wouldn't be hard to match up A, B, and C with A, B, and C down here. Actually, it would be a little hard. Notice why. What's the slope of little b? If I'm over here on the top left, let me zoom in a little bit just so we can get a little bit better picture here. What's the slope of A and B? Are they different?
No, they're parallel lines.
Exactly. So they have the same slope. So whatever that slope is, it looks to be about 1. Well, that's capital B. So both little a and little b's derivative is capital B.
Oh, it is? Okay.
Yeah, it's a slope of 1.
Regardless of its
It does not matter. It's positioning.
okay.
After it goes through the origin, does not matter. Remember what derivatives are. They're slopes. That's it. Okay? Now, D, now let's talk about C. What kind of slope is C? Little c.
Little c. That would be -1.
Which line is that under the caps?
Would it just be a?
Yeah. And finally, D, what's the slope of D?
1/2.
And which one is that?
B.
Okay. Now we're going to now we're going to do the same thing with these curves on the right. And you're going to notice something very key. What's the slope of a parabola have to be?
What do you mean?
It's got to be a straight line.
Yeah. And for a cubic function, it has to be a parabola.
Yeah, exactly. If we go back and look at this, notice that the derivative of the parabola is a straight line. And that's because if you start with a quadratic, when you take the derivative of it, you always reduce the power by 1. So instead of being a second degree polynomial, it becomes a linear polynomial. Always. So the derivative of all parabolas are straight lines. And just like the derivative of the cubic becomes a quadratic. In other words, when you take the derivative using the power rule, it always goes down. Every power of x goes down by 1. It becomes x squared plus x plus 9 or minus 9. Okay, so let's get rid of that. And so here's the parabola, which matches with the parabola.
I would probably have to go with B.
Has to be. It's the only straight line. Now let's see why. Because from there to there, it's decreasing. So the first derivative's in negative territory from there to there. But notice the first derivative slope is changing. In other words, it goes from like -1 to -1/2 to 0 as the slopes of the original function go from 1 to minus 1 to 0. And then from there to there, the original function is increasing. First derivative is positive. And do not, the hardest thing to do in calculus is to distinguish between positive and increasing. Okay? This red line is increasing from there to there, but it's negative. It's also increasing from there to there, but it's positive. So increasing and positive do not mean the same thing. Differentiate between the two.
Okay.
Okay. Now, this top little a, what kind of function is that? Is that linear, quadratic, cubic, quartic?
Would it be a cubic?
So what's its derivative going to be?
So it'd have to be a parabola.
Okay, so it's either capital A or capital D. And we can figure it out real quickly. What's the slope on the left-hand point?
It's negative. No, it's positive.
Slope.
It's positive.
Draw the tangent line. It's a positive slope. So therefore, are we talking about capital A or capital D?
Would it?
Here, let me draw on this so I can point out more. Okay, so we're looking at a positive slope, right? Right?
Right.
So its first derivative has to be what? Excuse me, I'm sorry, I'm confusing you probably. What we're looking at is an increasing function. Let's erase that. From here to here, it's increasing. Therefore, its first derivative has to be what?
Positive.
Only that is positive. That number right there is negative.
That makes sense to me now. Okay.
Good. And now you'll notice that as we go from here to there, its derivative is 0. That's going from there to there. The derivative hits 0. Then when the original function starts increasing again, we get positive again. Again, do not concern yourself with whether that's increasing or decreasing. It's just whether it's positive or negative. And it's positive everywhere except 0. Right there is the only place it's not positive.
Okay.
Right? Because right there, it's not positive either. It's 0. Okay?
Okay.
Now, let's see. We did this one and we did this one. Let's talk about this one. What kind of equation is that? What kind of function?
Is that a quartic?
Probably. In other words, because it's got one extrema there, it's got a flat spot there, it's got another extrema there. So it can always be one level higher than all of those extremas. In other words, a quartic can only have 3 local extremas. If I were to draw a graph like this, well, that's got an extrema there. 1, 2, 3, 4, 5, 6. That's going to be a 7-degree polynomial.
Oh, yeah, that makes sense.
Okay. You don't always have that many extrema. In other words, this point in the middle here is not really an extrema, but it's typical of a cubic function. In other words, the basic cubic function has a flat spot like that. But yeah, that's probably a quartic, which means its first derivative is what?
It would have to be a cubic.
Yeah, now, the only thing there that is a cubic is that bottom left.
Yeah.
That's not a cubic, that's a quartic. We got 1, 2, 3. So that's a quartic. So the question is, this must be 5th degree.
Huh.
Hold on a second. Let's see. We got 1, 2, 3. Looks like a quartic. Let me move this thing up a little bit. Now, hold on. I need to zoom down just a hair so I get them all in. Now I need to retake that picture. You can always figure it out by looking at the slopes at each point. Okay? What's the slope right there?
It's 0.
So one of these 4 red curves has to be 0 at -1. Well, it sure looks like that one. That's the only one that's 0 at -1 of the 4 red curves. That answers my question for sure, but let's continue on. So we are increasing. That point right there is 0 again. Notice that during that entire time that we're increasing, that's positive.
Why does it look like a little bump then, if it's just kind of...
Don't worry about that. The only thing that's important is that it's positive.
Okay.
Okay? In other words, you don't know what it's going to look like yet. You might at some point. But for the moment, just because it's increasing from there to there, its first derivative has to be in positive territory that whole way. And it is. There's a bump there. Well, we'll get to that. In other words, the slope there is close to 0. And then it starts getting steeper, steep. It's most steep somewhere in the middle there. And then it starts flattening out. In other words, this part from here to here is flattening out. The slope is becoming flatter and flatter. I'm drawing all over it, so it's kind of hard to see, but let me erase. But you can see if you were to take your cursor here, the slope is 0 right there, and it's 0 right there. And on our first derivative, it's 0 at those 2 points. But there's actually a point right here where it's the steepest, and that corresponds to that point right there.
Okay.
And by steepest, meaning that the first derivative has the highest value, and it does. That's why it's a peak. And then it starts flattening out again. Notice that from this x to 0, it starts flattening. It's getting less and less. So the first derivative goes back down again. And then this part does the same thing as that does. So it's definitely capital C goes with little b.
Okay. Well, thank you. That helped out a lot.
Yeah. Well, and you can't always do it. Yeah, I want to make sure I don't go over on you here. So I had to check my clock. One problem with using this program is it covers up my clock on my computer. I can't see it.
I have it.
So it's not so much determining whether you're looking at a cubic and then finding a quadratic, or that clearly has to be a 5th degree polynomial. Because, its derivative, this is at least a 4th degree polynomial on the lower left. It's got 3 peaks. That's a 4th degree polynomial. And just based on the power rule, if this is a 4th degree polynomial, then the one up above has to be a 5th degree. Okay? But that's not really the way to figure it out. The way to figure it out is to look at it, start with the left, and see what the slopes are doing. You can see, just kind of put a value on the slope as you move along the curve. And notice from the very beginning to that first point, the function is decreasing, and that's negative territory, as it should. And then from this point here down to this point, it's also decreasing. That's negative territory also. So that's really the way to do it, okay? And then finally, let's look at this one and see if we can figure out what the answer is. Again, I have no idea what degree polynomial that is. I can't tell by looking at it.
Mm-hmm.
But I can tell that it's decreasing the whole way, right? In other words, from this point to this point, the function is decreasing. So the first derivative has to be what? Through that entire domain.
Negative.
Done. It's the only one that's negative the whole way.
All right.
Okay. And it doesn't look like it, but the slope, yeah, it does look like it actually. Yeah, that slope's about -1, and that's about what that is, or -1/2 maybe. But the key is it's decreasing from there to there, therefore its derivative has to be negative the whole way. That's the only one that's negative the whole way.
All right.
All right. Let's see what we can do in 3 minutes here. These ones on the left, I think you get all of these. Am I correct?
Yeah, I did.
Okay. In other words, when everything's a straight line, the slope is constant throughout that whole line.
That's pretty.
A has a constant slope the whole way. Therefore, its derivatives are all going to be horizontal lines.
Mm-hmm.
All right. Now, let's see what we can get done with 10. Yeah, we've basically done 1 through 9. Now, the only difficulty here is, once again, we're online. What would be great is if you had a drawing tablet on your end, because GoToMeeting actually allows me to make you the presenter. So I could say, draw the derivative curve of that. Which is kind of impossible for me to do online. Because all I can say is, tell me where it starts, tell me whether it's positive or negative. What is the derivative curve from there to there? Positive or negative?
It's positive.
Okay, so from there to there, we have to be above the x-axis. Okay, and I can tell that I've got a fairly steep slope there, so let's make that a high value. But then that slope is flattening until I get there where it's 0. So it's got to go through there, the derivative curve. And it starts out high, and it is a parabola, so its first derivative is going to be linear. So that's the way the first part of it starts. The rest of it's also linear. So this is the first derivative curve of that. And one way to think about it is that that's a parabola. You know that when you take the power rule and apply it to a second degree quadratic, you get linear. It reduces that x squared down to x. So the derivative curve always of a parabola has to be a straight line. So the only thing you really have to do is figure out where it starts, where I kind of guessed at what that slope was. And the next key point is where the slope is 0, which is always the peak of the parabola, the vertex.
Mm-hmm.
That's always where your tangent line is horizontal, slope of 0. And then it's decreasing from there to there, so it's got to be in negative territory the rest of the way.
Okay.
All right. I guess we can stop there since it's 9.
Okay.
But you can kind of see how to do that one too. In other words, the derivative has to be positive between there and there.
Mm-hmm.
And then it's got to be 0 here. And then it's got to be positive from there to there. So the derivative curve has to be in positive territory except there where it's 0. And it looks to me like it's going to look something like this. See why?
Yeah.
Positive the whole way. And it's 0 right here. And that's the only place where the derivative is 0. And yeah, that's the absolute value function. And if I were to try to take the derivative of the derivative, it would not be differentiable right there. So most functions will reach a point where they're not differentiable at certain points. All right, I'm going to let you go.
Well, thank you. This actually helped a lot because this, like, when we were going over this today, it was so confusing.
Well, it is. The graphical part of this stuff is pretty confusing.
Yeah, it was overwhelming, but this helped a lot. So thanks again.
Well, good.